Welcome to Predicting Change. Our objective today is to develop your understanding and skill in using algebra to solve problems involving variables, like population that change as time passes. Let's look at the population change in Brazil. Brazil is the largest country in South America. Its population in the year 2005 was about 186 million. Census statisticians in Brazil can estimate change in that country's population from one year to the next using small surveys and these facts. Number one, based on recent trends, births every year equal about 1.7% of the total population of the country. So think about what that means. Births amount to 1.7% of the total population. And deaths every year equal about 0.6% of the total population. So first of all, is the population growing every year or decreasing based on these two facts? If you said increasing, you would be correct because there are more births than there are deaths. So how much of the estimated change in Brazil's population from 2005 to 2006 was due to births? Well, due to births, that was 1.7%, we said. And how about due to deaths? Deaths was 0.6%, so not even 1%. How about if we combine both? Pause the video and see what you get. Well, if we combine both, we have an increase of 1.7%, and we have a decrease each year of 0.6%. So that means if we combine them, we have an increase of 1.1%. But we want to know the actual numbers of people. How many people are we increasing by? How many are we decreasing by? What about combined? So again, pause the video, see if you can come up with how many births we have each year, how many deaths, and then the total population combined. For births, we would have taken our population, multiplied it by our percent to figure out what the increase is. 3.162 million people each year due to births. Notice that when I multiplied by the percent, I didn't multiply by 1.7. Remember, this is 1.7%. Percent means out of 100. So to turn it into a decimal equivalent, I would need to divide this by 100. I would move the decimal up 10, 100, and get 0.017. How about deaths? When I consider deaths, I have to consider that this is a decrease in population. So I took 186 million people times, now this time it's 0.006, because remember I have to divide by 100, so the decimal moves to the left 2 places, and I get 1.116 million here on my calculator. But I'm putting a minus here because this is a decrease in population. Now I can just combine these two in order to figure out what both causes are combined. So let's do that, and then we'll compare it to calculating a third way. When I combine these over here, our births and our deaths, I get a net population increase of 2.046 million, which if I added that then to my starting population of 186 million, after 1 year, I know that I would have 188.046 million people. But let's look at this third way down here. So I can do it by steps. Step 1, calculate my additions. Step 2, calculate my subtractions. And step 3 here, take the net. Or I can just look at this percent in order to calculate my difference. So if I have 186 million and I just multiply that by 0.011, I should be able to come up with this 2.046 number. So let's try that. 186 times 0.011 gives me that 2.046 number. So there's multiple ways to come to the net additions that we would have in population. Let's go ahead and look at a table now. We want to calculate estimates for the population of Brazil in all these years, 2006 through 2010. We want to record the estimates here in the table and the year-to-year changes as well. So we want to find the change, and remember we found the change back here this 2.046 multiple ways, and then we want to actually find our total new population, which is what we did when we added 186 million, our starting population, to our change. So pause the video and fill out a table like this on your own. And if you're done, if you'd like to, go ahead and make a plot on a graph, either by hand or online, plotting the year in the total population, and then see if you can describe the pattern of change over time and explain how the pattern you describe is shown in both the table and in the plot. Let's examine the table and see how you did. So we started with 186 million. We already calculated the change from 2005 to 2006 to be 2.046 million, which we added to that 186 to get 188. This becomes our new population in the year 2006. Well, we know that our change every year is 1.1%. That stays constant. That never changes. But our population does change each year in that it grows by that amount. So we would need to take 188.046 times our 1.1% or 0.011 to get a new value of 2.069 if I round. And then we would need to add that to our population that we started with for this year. So we have to be careful to always add it to our new population at the start of each year. And that gives us 190.115. And we would continue that down. We would now take the 190.115 and multiply that by 0.011. That will give me a new change of 2.091, and when I add it to the 190, I end up with 192.206. And then I would start over. 192.206 times 0.011, which is our change. When you're all finished, here's what our table should look like. Notice that our change, even though our percent stays the same, our change increases each year because our overall population grows a little bit more each year by that change. Notice this is a very slow change, but eventually over time it will be significant. So remember that births every year equal about 1.7%. Our deaths each year were about 0.6%, and we started with 186 million. Now let's consider what this would look like in a graphical form. In order to graph this, I use an online graphing calculator called Desmos. Here's the website up here, desmos.com. You can go there, or you can also put in /calculator. In order to graph this using this calculator, you merely just need to put in your coordinate points here into each of these spots, and then notice that each of these points then shows up here on your graph. If I look at this trend, this seems almost linear, very flat actually, but let's look at our window. So for our Y window, we have a pretty big expanse. We have to go from 0 all the way up to 200. So there's a lot of increments in between. How about for our x-axis? Well, let's go over here and look at that. We really only go from 0 to about 5. So the problem is here in our Y view. If we want to change that, we can go over here. Desmos has a window that we can change, and we can change our y-axis. We don't need negative 51.3. In fact, we really could start way up here at about 150 or maybe even 180, but I'll change it to 150 and see what happens. So now this is considerably shorter, but we want to see more depth of detail. Well, notice that we don't go above 200. So I'll go ahead and change my Y window to be 200 as the max. Notice what happens here. Now I have 150 down below and I go up to 200. But you can clearly see now that there's more depth. You can see the rate of change a little bit better. Example of our two tables shown with two different views, or two graphs I should say. Notice that with the first one it's hard to see that rate of change, but down here you can see that it's a little more steep and you get an idea of how it's changing. If we compare the table to our graphs, the table shows that the population change is increasing slowly from one year to the next. Notice how slowly it's increasing. Eventually, this will produce noticeable effects in the population. But for such a small percent growth rate in only a few years, the typical exponential upsurge will not be noticed. So in reality, this is growing at an exponential rate. If we notice the rate of change, we will not have a constant rate of change. It grows actually exponentially. But again, very difficult to see with these few years and with this window. The appearance of the plot of the total population data will depend, of course, as we just looked at, on the scales chosen and whether you want to keep 0, 0, the origin, in the view. Let's do one final test before we close for today. So given these four choices, which of these strategies for estimating change in Brazil's population from one year to the next uses the growth rate data correctly? Pause the video and see if you can answer the question. Well, hopefully you said that A was viable. We calculated it this way. We took 0.017 times our current population and we subtracted 0.006 of our current population to get our change. But we also did it this way too, as in B. We took the difference between these two and just multiplied that by the current population. If we look at the next two examples, they don't work. But why don't they work? We'll notice in C here that 0.17 isn't the correct use of our percentage. We need to write it as 0.017. Same thing with 0.06. That's really not 0.6%, that's 6%. And if we look at D, we have the same situation. We're using the percents rather than the decimal equivalent, so those two won't work. And that concludes our lesson today on predicting change.